Welcome everyone to chapter 7. I know a lot of you are probably ahead of this for the lab, everything else. We're going to get this, don't worry. Reactions in aqueous solution and aqueous equilibria acids and bases are what's going to be covered. You're going to note that I took some stuff out of chapter 6 and put it in chapter 7 notes just because honestly the book doesn't really make a lot of sense in the way that they order things. So I'm trying to keep it all in where it makes sense, at least for these videos. So you'll notice the notes have definitely changed. Suggested chapter problems, and here we go. So what is a solution in general? A solution, the term means a homogeneous or homogeneous, either way you say it, mixture of two or more substances. Those substances have terms. One is the solvent and one is the solute. The solvent is the one that is present in the largest number of moles, and it is what does the dissolving. So it does the dissolving. So a lot of times from just reading the questions, you can figure out which is the solvent and which is the solute. The solute is the one that's dissolved into the other one, and so it is dissolved, and it's present in the smallest number of moles. A lot of times these are really obvious, and especially when we're talking about aqueous solutions, but when we start talking about maybe an alloy is a solution of two metals. So maybe mercury is dissolved in lead or something like that. Or you have copper and zinc. These are common alloys that we have. But in general, those are when it gets to be a little bit more tricky and we want to use the term that says it's the largest number of moles or the smallest number of moles. If 161 grams of sodium carbonate are dissolved in enough water to make 4.6 liters of solution, what is the solute and what is the solvent? So are dissolved means it is dissolved, right? So this would be the solute. And if we look at the terms for water, it's dissolved in enough water means it's the solvent. So the solute would be sodium carbonate and the solvent would be water. So it's just as simple as reading the question in this case. We don't actually have to figure out moles. We could, but we don't have to. So concentration. Concentration is something that you're probably learning a lot about during COVID-19 because you're probably taking cleansers and diluting them down. So if we wanted to make a bleach solution, a 10% bleach solution will kill the COVID. So that means we're dissolving it 1 to 10 or 10 milliliters for every 100 milliliters. We're making a 10% bleach solution. And then you leave it on for 10 minutes and it will disinfect the area. So there's a difference between being clean and disinfecting one. I hope you guys are learning that if you did not already know that. So concentrated means, in qualitative terms, concentrated means it's going to be more solvent, more solute than solvent. So this would be a concentrated solution. It's darker, that's thicker, things like that. So if you have the bottle of soap and you take a cap full and pour that into the gallon of water, you're diluting it. So this would be a dilute solution. So there's fewer solute particles per volume of solvent. So we're looking at these in qualitative terms. Qualitative means no number and unit. We're talking about them in terms of physical characteristics. But we can talk about them in quantitative terms. And we do, and we will. So you're going to be expected to be able to do this. So molarity is the term we use for that. Molarity. Molarity means, so what does it mean? It means moles divided by liters. So this is molarity. It is also something you can calculate. What is molar mass? If you don't have that one down, we're going to be worried. So molar mass is grams per mole, per 1 mole. Molarity is moles per liter. So we can calculate these. And these will be something that we can use to transition. So just like I can use molar mass to go between moles and grams, I can now use the term molarity to go between liters and moles. The thing is with molar mass, this is always constant. for a compound. Molarity changes all the time, depending on who made the solution, and if it was made properly, all those things, it's going to change. So this isn't going to be something that you can just calculate once. We're going to have to calculate it all the time. So the symbols are a capital M. I hate to say it, but it's extremely important that this is a capital M because there is another term called molality, which is a lowercase m, and it is equal to moles of solute over kilograms of solution. Now, in an aqueous solution or a water solution, they should be equal. So molality is often used to determine what we call colligative properties. We're not going to get into that this semester. But that would be like freezing point depression or boiling point elevation. I spelled elevation wrong. Did you ever hear somebody say, oh, add salt to the water, it'll boil faster? That's not right. It's actually going to take longer to boil, and it depends on how many salt molecules are in there. Also, salt molecules, Mrs. DeVos. Okay. Ions from the salt. I'm tired. Also, freezing point depression would be something like you see people putting salt on the road. They're putting salt on the road to lower the freezing point of water. You also use things like this in your radiator. You put a substance into your radiator. You don't just put water in your radiator. You put antifreeze, and the antifreeze lowers the freezing point so that it doesn't freeze and take up more space than your radiator can and expand and break your radiator. So that's what molality does. Molarity would essentially be the same thing, but we use kilograms in that case instead. So molarity, capital M, molality, lowercase m. Yeah, I know, it's confusing. So these are called square brackets. Square bracket notation. And there's an I there. So if I wanted to say the concentration of magnesium chloride is 0.25 molar, that's how I would write it. So when I read this, it means the concentration of, and that's how you would read it. But you just put the square brackets there and everybody knows what you mean, and that way we don't have to write all of those words. Molarity is an equation we can solve. Molarity is moles over liters. But I can solve this for any one of those variables, right? I can solve for liters and I can solve for moles. Just like that nifty triangle you guys like to make for density, which I totally never remember. So I believe it's molarity in this one, and then I think that's the triangle, what it would be, but you know, use at your own risk. And again, we shouldn't need a triangle at this point. This is just basic algebra, so I'm pretty sure you can do it without the triangle. If a solution contains 0.755 moles of sulfuric acid per liter, we can say that the molarity is 0.755 moles per liter. So we would say 0.755 molar sulfuric acid. So this would be read as molar. Yeah, just like your tooth. So a 0.755 molar sulfuric acid solution is how you would read that sentence. So volumes must be in liters. If they're not in liters, you have to convert. So remember, there are 1,000 milliliters in 1 liter, because that's probably your most common conversion you'll have to do. Molarity is a per expression, per liter, so moles per liter. Calculate the molarity of a solution prepared by dissolving 45 grams of potassium iodide into a total volume of 500 milliliters. All right, so we need what molarity is, moles over liters. Well, we don't have moles and we don't have liters, but we have grams and we know it's potassium iodide, so we can use the molar mass to calculate moles on the top. And on the bottom, we can convert milliliters to liters. So 45 grams of potassium iodide. And the molar mass of potassium iodide is So there are 166.0 grams of potassium iodide in 1 mole of potassium iodide. So 45 divided by 166 is 0.27108. 43373 moles of potassium iodide. And 500 milliliters, there are 1,000 milliliters in 1 liter. So 500 divided by 1,000, we move the decimal place 3 places, so it's 0.5000 liters. And then we divide the two because molarity is moles divided by liters. So 0.27108433373 moles divided by 0.5000 liters. Zero 0.5421686,746. Significant figures, there are 4 sig figs here, 4 sig figs here, 4 in our answer. So if I change colors here, 1, 2, 3, 4, look 1 to the right. Our final answer would be 0.5422 molar potassium iodide. Okay, let's try another one. Determine the molarity of a 5-liter solution that contains 235 grams of sucrose. So 5 liters, molarity is moles over liters. We have liters. We have 235 grams, so we need to convert that to moles. We all know how to do that, so let's do that. 235 grams of C12H22O11. So take the molar mass, add that together, you should get 342.30 grams of C12H22O11 for 1 mole. And when you do that math, you should say, who stole my calculator? But if nobody stole your calculator, you should get something like 0.687. Roughly, let's see, 235 divided by 342.3, 0.6865322.816 moles. And then we say, so that's 0.687 moles. I'm just going to round it for now because why not, right? COVID. Okay, H22O11. And then we're going to take that and put that into the molarity equation. 0.687 moles divided by 5.00 liters. And we get 0.1373064.563. If you're finding that you're getting a different number than what I just got, I did not round this in my calculator. So that is why. We round this now and we get 0.137 molar sucrose, or C12H22O11. 3 significant figures for both those numbers, so that looks good. All right, good. So here's the answer within the PowerPoint, because I've got to click through anyway. How many milliliters of 3.50 molar sodium hydroxide can be prepared from 75 grams of solid NaOH? How many milliliters? Let's see. Molarity equals moles over liters. We have a 3.50 molar sodium hydroxide solution, so we have molarity. And we have 75 grams, which we can use to find moles. So we have moles. We want to find liters because it says how many milliliters, and then we'll convert that to milliliters. So we need to solve this equation for liters. So liters times molarity equals moles, and then divide both sides by molarity. You get liters is equal to moles divided by molarity. So we need moles, so let's start there. So 75 grams of sodium hydroxide, Sodium hydroxide would have a mass of 40, something like that, 22.99 plus 16 plus 1.008. It really depends on what values you use. 39.998 grams of NaOH for 1 mole. If you use 40, it's not going to make much difference here. 75 divided by 39.998 gives you 1.875093755 moles of NaOH. So moles divided by molarity, so we get liters is equal to 1.875093755 moles divided by the molarity, which is 3.50. Now remember, it says molar. I'm going to say moles over liters because it's the same thing. Just to show you how the moles cancel, the liters are in the denominator, so they're actually in the numerator. So we're going to end up in liters. So divided by 3.50, 0.5357410728. That's liters. And for every 1 liter, there are 1,000 milliliters. So multiply that by 1,000, and you get 535.7410728. That's milliliters. How many milliliters of 3.50? So we need 3 sig figs here, 4 sig figs here, so 3 in our answer. 536 milliliters. Now you have to ask yourself for the label, does it matter what the molarity is? Yeah, because if I were to use 4 molar or 8 molar, I wouldn't need 536 milliliters. I would need a different amount. So 536 milliliters of 3.50 molar sodium hydroxide. So the molarity does matter. So you need to have that concentration written in there because it would change the answer if it was different. Dilution. So a dilution equation is going to tell us where we're taking a concentrated solution and making a less concentrated solution. Normally that's the way we go. Technically, you could also boil off some of the liquid and become more concentrated. But in general, you will use this a lot if you're going to be doing any biological sciences or anything, because we do a lot of serial dilutions, and diluting the concentrated, then diluting the dilution that you made, and then diluting that dilution. That's called a serial dilution. So you want to make sure you're doing this properly, because if you mess this up, then everything gets messed up. So you really want to make sure you're paying attention and that you know what you're doing when you do these types of things, because it'll be something mundane that you do all the time. So MCVC is equal to MDVD. Now this just means molarity of the concentrated times the volume of the concentrated is equal to molarity of the diluted times the volume of the diluted. I changed it to that from from C1V1 is equal to C2V2 because my students were trying to figure out which one's 1 and which one's 2. So by labeling them concentrated versus dilute. Also, which one do we keep together? So when I was younger, we didn't have STIs or STDs, we had venereal disease. So we had VD. So if you have VD, you should go see an MD and those stay together. Ha ha ha. So this is what this means, and I just told you what they mean. So we're going to make sure the units are equal. They don't have to be in liters, they could both be in milliliters. As long as they're both the same, you can keep them. A chemist wants to prepare 0.8 liters of a 0.15 molar sodium chloride solution. The stock solution is 6 molar sodium chloride. How much of the stock solution should she add? So how many milliliters should she add? So I like to make a little list: MC, VC, MD, VD, and then figure it out from looking at the problem. So a chemist wants to prepare, so she wants 0.80 liters of a 0.15 molar solution. She has a 6 molar solution, so this one is obviously more concentrated. So that's the concentrated molarity, 6.0 molar. We want to know how much of that stock solution she needs to add. So this is going to be our question mark. How many milliliters? The molarity of the dilute solution is 0.15 molar, and we would like 0.80 liters of that solution. So these two stay together and these two stay together. So MC VC is equal to MD VD. We want to solve for VC, so we divide both sides by MC. And we get VC is equal to MD VD divided by MC. So 0.15 molar times 0.80 liters divided by 6.0 molar. The molarities cancel. We're going to be left in liters. So let's take our handy dandy calculator. 0.15 times 0.8 divided by 6 is 0.02. But that's in liters, and we wanted to know how many milliliters. So in 1 liter, there are 1,000 milliliters. So we would multiply that by 1,000, and we get 20.0. I mean, it's going on. So how many sig figs? We're going to need 2. So we would need 20 milliliters of 6.0 molar sodium chloride. What is the molarity of the solution prepared by diluting 25.71 milliliters of this molarity of 0.0760? So it says by diluting. So that means this is the concentrated. So what is the molarity of a dilute solution? So we're talking about diluting. So we're looking for the molarity of a dilute solution. We're taking 25.71 milliliters of the concentrate, and that has a molarity of 0.07060. And we're going to bring that up to 500 milliliters. So MC VC is equal to MD VD. We want to solve for MD, so we're dividing both sides by VD. So MD is equal to MC VC divided by VD is equal to, let's see, 0.07060 molar, 25.71 milliliters divided by 500 milliliters. Milliliters cancel. So 0.07060 times 25.71 divided by 500 is 0.003630252. Sig figs. See, we have 4. So 1, 2, 3, 4. 1 to the right for rounding. 0.003630 molar sodium chloride. What volume of 12 molar hydrochloric acid must be used to prepare 175 milliliters of 0.980 molar hydrochloric acid? So this is obviously more concentrated, so this would be the molarity of the concentrated. So MC VC is equal to MD VD. 12.0 molar. VC, what volume of that do we need? So we're looking for that volume. MD, this is the molarity of the dilute, 0.980 molar, and we need 175 milliliters of that. So MC VC is equal to MD VD, and we want to solve for VC, so we divide both sides by MC. So VC is equal to MD VD divided by MC, and that would be 0.980 molar times 175 milliliters divided by 12.0 molar. $14.2916666667. We'll just say that's repeating. But just in case you're superstitious, I just kept going with the sixes. All right, so we're going to round that to three significant figures. So 14.3, and this is milliliters. But milliliters of what? Remember, we always have to, if we have a volume unit, say what concentration we're using. Of 12.0 molar hydrochloric acid. Because if it wasn't 12 molar, if it was 6 molar, we would need double that. So, what is the molarity of a dilute solution? So we're talking about diluting. So we're looking for the molarity of a dilute solution. We're taking 25.71 milliliters of the concentrate, and that has a molarity of 0.07060. And we're going to bring that up to 500 milliliters. So MC VC is equal to MD VD. We want to solve for MD, so we're dividing both sides by VD. So MD is equal to MC VC divided by VD is equal to, let's see, 0.07060 molar, 25.71 milliliters divided by 500 milliliters. Milliliters cancel. So 0.07060 times 25.71 divided by 500 is 0.003630252. Sig figs. See, we have 4. So 1, 2, 3, 4. 1 to the right for rounding. 0.003630 molar sodium chloride. What volume of 12 molar hydrochloric acid must be used to prepare 175 milliliters of 0.980 molar hydrochloric acid? So this is obviously more concentrated, so this would be the molarity of the concentrated. So MC VC is equal to MD VD. 12.0 molar VC. What volume of that do we need? So we're looking for that volume. MD, this is the molarity of the dilute, 0.980 molar, and we need 175 milliliters of that. So MC VC is equal to MD VD, and we want to solve for VC, so we divide both sides by MC. So VC is equal to MD VD divided by MC, and that would be 0.980 molar times 175 milliliters divided by 12.0 molar. $14.2916666667. We'll just say that's repeating. But just in case you're superstitious, I just kept going with the sixes. All right, so we're going to round that to three significant figures. So 14.3, and this is milliliters. But milliliters of what? Remember, we always have to, if we have a volume unit, say what concentration we're using. Of 12.0 molar hydrochloric acid. Because if it wasn't 12 molar, if it was 6 molar, we would need double that. So notice we didn't use any mole ratios. There were no equations in those. Those are called dilution equations. Those are not solution stoichiometry. So what we're going to talk about next is titration and solution stoichiometry. So one of the things that happens a lot is students use the dilution equation when they should not use the dilution equation. So the dilution equation is something you use when you're only given one substance, no equation, so no chemical sentence, and you're only asked about one type of substance, and we don't need to use mole ratios. So a titration is a specific chemical test that we're going to do. Actually, you didn't do, you looked at the data for, where we're adding a known concentration, so a standard, to another solution that's of unknown concentration. And when we do that, we're going to figure out what the unknown concentration is. So standardization is something that we do to make sure that our standards are a known concentration. If they're not a known concentration, we're really not doing anything. Then there are terms equivalence point, end point. These we want to be equal. So we want to end our titration at the equivalence point. But what are they? The end point is just whenever I stop. So whenever I stop the equation, whenever I stop the titration, that is my end point. I would like to stop the titration at the equivalence point. The equivalence point is when they are chemically equal, when they're mole ratios, when they're chemically equal. And that means I'm going to be ending it where they are chemically equal, and then I can do some math based on that thought. So the indicator is what I use. The indicator is usually a weak acid or a weak base. And that weak acid, so if we're using a weak acid, the weak acid would be a different color than its conjugate base. And if we're using a weak base, the weak base would be a different color than its conjugate acid. So when we're doing this, we have these pairs that work together and that are color sensitive to pH. And pH is going to tell us and signal the endpoint. So we're going to look at that by noticing the color change. So this is phenolphthalein, an indicator. It's clear. So it's clear here, and then what happens is eventually it's going to turn pink. When it stays that shade of pink, you'll know that your titration is over. And you don't want to add too much. You want to keep it within 1 drop can make a huge difference. So we want to make sure that we're right on, because that'll tell us when we get to the end point is when we stop, right? So we want to stop at the equivalence point. So we have to go slow. And I'm really bummed that you guys aren't going to get a chance to try this in lab, because this is something that it's good to practice your technique in lab. So how many grams of lead 2 iodide, so this is lead 2 iodide, how many grams of this will precipitate when excess potassium iodide solution is added to 50 milliliters of 0.811 molar lead 2 nitrate? This is so similar to what you were doing before. You were doing this all along, but you were doing it when you were given grams, so that you were given grams before. Now you're given a molarity and a volume. So being given a molarity and a volume in liters, you can get to moles. Because remember, when we're in moles, that's our chemistry oyster. We can go anywhere from there. So these problems are no different than the ones you just did in chapter 6 with the stoichiometry, but now we're doing it with solutions. So the only thing we have to do differently is how we get to moles originally. So you're going to notice the math is very similar, except this first step, how we get to moles. But you already know that molarity times liters is equal to moles. So I'm going to convert the 50 milliliters to liters. We can do that right away in the dimensional analysis. So 50 milliliters of lead 2 nitrate. So for 1,000 milliliters, there's 1 liter of lead 2 nitrate. Now I'm in liters, liters times molarity. Now watch what I'm going to do, because molarity is equal to what? Moles over liters. So I'm going to say for every 1 liter of this solution here, 1 liter, there are 0.811 moles of lead 2 nitrate. So all I did was take the molarity, the 0.811 moles over 1 liter. And I put that into dimensional analysis. So this is just the molarity. Just like we've been doing with molar mass, everything, it's just written in dimensional analysis, so it looks a little different. So liters cancel. I'm in moles of lead 2 nitrate, but I want to know about lead 2 iodide. So 1 mole of PbNO3, 2 gives us 1 mole of PbI2. So this part from here on out is the same that we've been doing. And 1 mole of PbI2 has a mass of, it is 461 grams of PbI2. Okay, none of that part's changed. So after here, this is all the same as chapter 6 that we just did. So let's do this in our calculator. 50 divided by 1,000 times 0.811 times 1 divided by 1 times 461 gives us 18.69355 grams. So these cancel. So we're going to need 3 significant figures, so 18.7 grams of PbI2. That's how easy it is. So it's really very similar to what you just did. The only difference is how you got to moles. No problem, right? We can do that. Now, we only gave you one, just like we did in chapter 6 when we started. We only got information about one thing. This is not a limiting reactant problem. We said this one is an excess. So we're going to take a look at this. Is what happens. What volume in milliliters? So what volume in milliliters of 0.4050 molar calcium chloride reacts completely with 25 milliliters of 0.2800 molar silver nitrate? So this is a little bit more confusing because we're not asked about grams. So this one's probably a little bit more confusing, but we always start where we have the information to find moles. But I can't find moles here. Can't find moles. But here I can find moles because I have 2 pieces of information. So I need to start where I'm given enough information to find moles. So 2 pieces of information, info, so it would need to be a molarity and a volume. So I have the volume, but it's in milliliters, so 25 divided by 1,000. So we're going to start this with 25 milliliters of silver nitrate. There are 1,000 milliliters in 1 liter. That's just a unit conversion. For every 1 liter, so this is going to be our molarity step. I'm going to make this is molarity of AgNO3. I'm going to write that in dimensional analysis. So for every 1 liter of AgNO3, I have 0.28, that's an 8, 00 moles of AgNO3. You see what I did there? Because 0.2800 moles of AgNO3 for every 1 liter. That's what molarity means. So now I've converted from liters to moles, and now I'm going to convert from moles of AgNO3. So this next step is the mole ratio step. I'm going to go from moles of AgNO3. So how many moles of AgNO3 to moles of the question mark, to moles of calcium chloride. So this one is a 2, and this one is a 1. So this one is a little different than the stoichiometry we did in chapter 6, because now, instead of going to grams like we did in the last problem, we're actually going back to a volume. So instead of needing the molar mass here, we're going to need another molarity step. Just a different conversion, some new conversion that we're using. So instead of going from moles to grams, we're going to go from moles of calcium chloride to liters. And remember, molarity is always per 1 liter because we did the math. So there are going to be 0.4050 moles of calcium chloride for every 1 liter. Now this is going to give you to liters. We want milliliters. And there are 1,000, or 1 liter, there are 1,000 milliliters. Okay. Now you probably see, some of you, that I did this divide by 1,000, multiply by 1,000, but that's how the units work. So I'm going to keep it that way. I'm not going to change it. So 25 divided by 1,000 times 0.2800 divided by 2 divided by 0.4050 times 1,000 is 8.641975309. Right, this is milliliters. And let's see, sig figs, I should have 8.642 milliliters of 0.4050 molar calcium chloride. And anytime I answer in a volume, I need to have that molarity in the answer. How many grams of silver bromide can be prepared when 58 milliliters of, so 58.0 milliliters of 0.264 molar silver nitrate reacts with excess magnesium bromide? So give it a try. If you haven't done it, pause it and try it. This is not a new one. We've done one just like it the first problem we did. So 58.0 milliliters of silver nitrate So we're going to convert from milliliters to liters. So 58 milliliters, there are 1,000 milliliters in 1 liter. So now we put our molarity step in. For every 1 liter of AgNO3, there are 0.264 moles of AgNO3. And there are 2 moles of AgNO3 for every 2 moles of silver bromide that's formed. And 1 mole of silver bromide has a mass of, should have calculated that, 107.87 plus 79.9, 187.77. So 58 divided by 1,000 times 0.264 times 2 divided by 2 times 187.77. And that will give you 2.87513,424 grams. And we need 3 sig figs here, so 2.88 grams of silver bromide. So that's how much is going to precipitate out. Good. How did it go? Well, I hope it went well. We're going to keep doing some more. If 205 milliliters of a magnesium bromide solution, 205 milliliters, react completely with 42.95 milliliters of 0.439 molar silver nitrate, what must be the molarity? So what is the molarity of the MgBr2 solution? So this is pretty similar to the one that we did, the second one that we did, but I just want to remind you that molarity is moles divided by liters. Now here, we want to know the molarity, so we need to know moles and we need to know liters. We have the volume, so we can find the liters. We need to convert this to moles. So we need to find moles of magnesium bromide by starting with the information about silver nitrate. So just like we've done for a while now, 42.95 milliliters of silver nitrate. There are 1,000 milliliters in 1 liter. 1 liter. So just a unit conversion. For every 1 liter of the silver nitrate solution that we have 0.439 moles. Now we just do the mole ratio, so 2 moles of AgNO3 gives us 1 mole of magnesium bromide. So this is going to give us moles, and that's what we need, moles of magnesium bromide, and then we'll divide them out. So 42.95 divided by 1,000, we multiply that by 0.439, and we divide by 2. We get 0.009427525 moles, and 205 milliliters divided by 1,000 milliliters is equal to 1 liter. So 205 divided by 1,000 is 0.205. So we divide that by 0.205 liters, and we're going to get molarity. .04598799268. 3 significant figures, 0.0460 molar magnesium bromide. Oh, I can't. There we go. How many milliliters of 0.0947, so how many milliliters of 0.0947 molar sodium hydroxide would be required to neutralize 20 milliliters of 0.1033 molar sulfuric acid? So we're going to be looking for milliliters here. So we'll start with 20.0 milliliters. We convert to liters, so 1,000 milliliters in 1 liter. Now we're going to go to moles. So this is just a unit conversion. So for every 1 liter of H2SO4, this molarity tells me I have 0.1033 moles of sulfuric acid. For every 1 mole of H2SO4, I have 2 moles of sodium hydroxide. Now, this is the step that usually throws people for a loop because it's a little different. We're going to be going to liters because we're going to be converting using a molarity. So we're going to get rid of moles of NaOH and go to liters of NaOH using the molarity. So there are 0.0947 moles for every 1 liter. That's what molarity means. So that's a molarity step. And then for every 1 liter, there are 1,000 milliliters. 20 divided by 1,000 times 0.1033 times 2 divided by 0.0947 times 1,000 is 43.63252376. Or, let's see, 3 sig figs, 43.6 milliliters of, remember the molarity is important here, 0.0947 molar sodium hydroxide. These are really important in the sense that if I know what I want to do, how much I want to neutralize, I know what I have to bring to the party. So I don't need to start with 4,000 milliliters of this sodium hydroxide if I only need 50 milliliters. So this is a good way to start. Figure out what you might need if you know the approximate molarity. How many milliliters of 0.1157 molar sulfuric acid would be required to neutralize 29.64 milliliters of 0.1072 molar sodium hydroxide? This is very similar to the question we just did, so please pause it and try it. And I'm going to go through it. 29.64 milliliters of sodium hydroxide, 1,000 milliliters for 1 liter, and every 1 liter of sodium hydroxide, in this case, has 0.1072 moles of sodium hydroxide. Now we're in moles. We can go from moles of NaOH to moles of sulfuric acid. So this is 1 and this is 2. Now we want to know how many milliliters, so we're going to go from moles, so 0.1157 moles of sulfuric acid for every 1 liter of sulfuric acid using that particular solution. And 1 liter is 1,000 milliliters. So that gives me 13.73123596 milliliters. We need 4 sig figs in this one. So 1, 2, 3, 4, 13.73 milliliters of 0.1157 molar H2SO4. Good, I hope it's going well. We're just going to keep trying these, keep practicing them. That's how you're going to get it. If 30 milliliters of 0.150 calcium chloride, so 30 milliliters of 0.150 molar calcium chloride is added to 15 milliliters of 0.100 molar silver nitrate, what is the mass in grams of silver chloride that's produced? Wow, this is different, isn't it? Huh. But is it really that different from things you remember from last chapter? So I'm given enough information here, I can find moles. I'm given enough information here, I can find moles. And I'm asked about a product. So what type of problem is this? This is a limiting reactant problem. So we're going to have to do this twice. We're going to go from here to there, and we're going to go from here to there, and we're going to see which one produces the least, right? So let's start either way. So 30 milliliters, oops, still recording, I think, calcium chloride. Unit conversion to liters. In this particular solution, there are 0.15, excuse me, I meant to put 1 liter there. Still kind of weirded out that the screen just blinked on me, and I'm kind of wondering, I just want to make sure it's still recording. All right, so for every 1 liter of the calcium chloride solution, there are 0.150 moles of the calcium chloride. Now, for 1 mole of calcium chloride, we will get 2 moles of silver chloride that are going to precipitate out. And for every 1 mole of silver chloride, we have to get the mass of that, 107.87 plus chloride is 35.45. So every 1 mole of silver chloride has a mass of 143.32 grams. So 30 divided by 1,000 times 0.150 times 2 times 143.32 is 1.28988 grams of silver chloride. Starting with the silver nitrate, we have 15 milliliters. There are 1,000 milliliters in 1 liter. So we have for every 1 liter of silver nitrate, 0.100 moles of silver nitrate. Now we do the mole ratio. For every 2 moles of AgNO3 that react, we get 2 moles of silver chloride, and every 1 mole of silver chloride has a mass of 143.32 grams. 15 divided by 1,000 times 0.1 times 2 divided by 2 times 143.32 is 0.21498 grams. So which one is least? This is our limiting reactant. This is our excess reactant. So our theoretical yield then is, to 3 significant figures, 0.215 grams of silver chloride. So very similar to what we did in Chapter 6, just a different way to start by finding moles with molarity.